KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we start with example 5 problem. So in our previous class regarding the alternating current numericals, we discussed 4 example problems in our previous class, right? So example 1 to example 4. So in continuation to that, we have to start with example 5. Right. See here. First to see the problem, as numerical problem, then we will go for solution. Right. See here. A light bulb and an open coil inductor. A light bulb and an open coil inductor are connected to an AC source. See this, I am showing 2 devices also. You please be concentrated here. It is a circuit, right? It is the circuit, and he is saying how the circuit is arranged. So what are the things which are present and how they are connected, right? That he is saying. See this, a light bulb and an open coil inductor. A light bulb and an open coil inductor are connected to an AC source. You know the symbol of AC, right? This is the symbol of AC. Connected to an AC source through a key. This is the key. Through a key as shown in the figure, right? Okay. He didn't ask anything, but simply he told how they were connected, right? Now, the switch is closed. The switch is closed, and after some time, an iron rod is inserted into the interior of the inductor. You please try to catch up the situation what he is saying. It is very important to solve the problem. The switch is closed after some time. You know very well, when we close the switch, current starts to flow in the circuit, right? It's a basic phenomena, you know very well. First, we are going to close the switch. After some time, an iron rod is inserted here. You know, it is like a spring. What is inductor, right? And what is the energy stored in an inductor? That and all we discussed in our theory class. Now, in this situation or in this regarding this circuit, first we are going to close the switch. After some time, an iron rod is inserted into the interior of the inductor. Full stop. The glow of the light bulb A increases, B decreases, C is unchanged. As the iron rod is inserted, give your answer with reasons. As the iron rod is inserted, give your answer with reasons. Okay, right. So what he is saying is, a light bulb and an open coil inductor. A light bulb and an open coil inductor are connected to an AC source. Through a key. As shown in the figure, right? The switch is closed. After some time, an iron rod is inserted into the interior of the inductor. Then what happens to the glowing of the light bulb? Whether it is increases or decreases or remains unchanged or is unchanged as the iron rod is inserted. Give your answer with reasons. Give your answer with reasons. Okay, so for everything you have to give reason, right? So in this problem, the example 5 problem, first he is saying what is there in the picture, and then he is saying the situation when the switch is closed, what happens, and afterwards he is asking the reason for glowing of light bulb, whether increase or decrease or unchanged, and what is the reason. That's what he is asking. Okay, right. Now solution. See here, as the iron rod is inserted, the magnetic field inside the coil magnetizes the iron, increasing the magnetic field inside it. Please try to understand, please try to observe first what's going on. As the iron rod is inserted, the magnetic field inside the coil magnetizes the iron, increasing the magnetic field inside it. You know very well what is inductor, a device which stores energy in the form of magnetic field, right? What is a cell, what is a capacitor, what is inductor, and what is the basic difference regarding the functioning of these 3 devices I told you. Okay, here we had inductor. That's why, you know, inductor is a device which stores energy in the form of magnetic field. Okay, right. As the iron rod is inserted, the magnetic field inside the coil magnetizes the iron, increasing the magnetic field inside it. Full stop. Hence, the inductance of the coil increases. Full stop. Consequently, the inductive reactance of the coil increases. See here, the inductive reactance of the coil increases. As a result, a larger fraction of the applied AC voltage appears across the inductor. So because of all these things, what happens from here to there? As a result, a larger fraction of the applied AC voltage appears across the inductor, leaving less voltage across the bulb. So when there is less voltage, automatically you can expect what happens to the glowing of light bulb. It will be decreased. Okay, see here, as a result, a larger fraction of the applied AC voltage appears across the inductor, leaving less voltage across the bulb. Therefore, the glow of the light bulb decreases. Okay, so even the solution also you have to see step by step. So what he is saying here, as the iron rod is inserted, the magnetic field inside the coil magnetizes the iron, increasing the magnetic field inside it. Hence, the inductance of the coil increases. Consequently, the inductive reactance of the coil increases. Okay, as a result, a larger fraction of the applied AC voltage appears across the inductor. This is what the inductor I already showed to you is a bulb, and it is the AC source, and it is a switch. Okay, so when large amount of AC voltage, see here, a larger fraction of the applied AC voltage appears across the inductor, then only little is balanced, no? So leaving less voltage across the bulb. Therefore, the glow of the light bulb decreases. Okay, right, full stop. So this is what example 5. So in example 5, what he is saying is, a light bulb and an open coil inductor are connected to an AC source through a key. through a key as shown in figure. Right. The switch is closed after some time. The switch is closed after some time. An iron rod is inserted into the interior of the inductor. Please try to understand, first switch is going to close, then automatically current starts to flow. At this time he is inserting an iron rod through the inductor. Then what happens to the glow of the light bulb? So already we discussed the solution also, so it will be decreased. But anyhow, so the glow of the light bulb will increases or decreases or unchanged as the iron rod is inserted. Give your answer with reason. So what is the reason for decreasing the light bulb glow? The glowness of the glowing of the light bulb decreases. Why it is going to decrease? The reason is a larger fraction of the applied AC voltage appears across the inductor, leaving less voltage across the bulb. For this situation, what is the reason? You have to go back. See here. As the iron rod is inserted, the magnetic field inside the coil magnetizes the iron, increasing the magnetic field inside it. Hence, the inductance of the coil increases. Consequently, resultantly, the inductive reactance of the coil increases. Okay. So like this problem helps us to understand the situation. Okay. In the NEET exam or JEE mains exam, so like these problems will come. I am not sure about the same problem, but like this problem means having like this circuit, inductor or bulb and AC like this. So when we are solving this problem, the idea what we are learning here, the point what we are observing here is important while solving the problem related to this type of network, this type of circuit. Right. Next problem. Example 6. Example 6. See here. A resistor of 200 ohms. A resistor of 200 ohms and a capacitor of 15 microfarad. You know the value of micro, which is 10 to the power of minus 6. 15.0 microfarad are connected in series. To a 220 volts 50 Hz AC source. Right. So it is the potential difference across the source and it is the frequency of the AC source. You know what is the difference between AC current and DC current? Right. In AC current, frequency is present. It's a basic difference. In DC current, we can't expect any frequency. So that's why here they have given the frequency of source also. At the same time, this value also needed for us to get the answer for the thing what he is asking. Okay. Right. See here. A resistor of 200 ohms and a capacitor of 15 microfarad. 15 microfarad are connected. Are connected in series. To a 220 volts 50 Hz AC source. Full stop. This is the situation what they have given. So two things are there. Resistor and capacitor. Resistor and capacitor are connected in series to an AC source. Is the resistance of a resistor, is the capacitance of a capacitor, and it is the voltage applied across AC source, and it is the frequency of AC source. Now A. Calculate the current in the circuit. Right. So first we have to calculate current in the circuit. Next B. Calculate the voltage across the resistor and capacitor. Right. So we have to calculate voltage across the resistor and the capacitor. Okay. Right. Now, is the algebraic sum of these voltages more than the source voltage? He is asking whether it is more or not. If yes, resolve the paradox. So you know very well in physics we come across like this situation many times. If yes, we have to give the reason, we have to discuss. Right? If not, that will be different situation. Okay. So in this example problem, they have given two things. Okay, regarding the numerical values, they have given 4 things. Is the resistance of a resistor, capacitance of a capacitor, which are connected in series to the AC source, and it is the voltage applied across the AC source, and it is the frequency of the AC source. Now, He is asking to calculate the current in the circuit, right? And he is also asking to calculate the voltage, that is what RMS voltage. Root means square. Calculate the voltage, root means square voltage across the resistor and the capacitor also. Now the question is the algebraic, you know very well, voltage means it is a potential difference, is a scalar quantity. That's you keep in mind. Is the algebraic sum of these voltages. So you don't consider the direction, I mean in which direction the charge is flowing, that and all. Simply he is taking that algebraic sum of these voltages more than the source voltage, right? If S, resolve the paradox. If S, resolve the paradox. Okay, right. See here. See the solution. First we have to write the given values. We have to write the given values. Okay, given capital R is equal to 200 ohms. C is equal to 15 microfarad. That is equal to 15.0 into 10 to the power of minus 6 farad. So micro means 10 to the power of minus 6. No, that only he is writing here. R is equal to 200 ohms. C is equal to 15 microfarad. That is equal to 15.0 into 10 to the power of minus 6 farad. V is equal to 200 volts. V is equal to 200 volts and nu is equal to 50 Hz. Nu is equal, that is the frequency. Just by using usual notations, that is R for resistance, C for capacitance, V for voltage, nu for frequency. Just by using usual notations, he replaced, he has written all the given quantities. Now, there are two things now, A and B. First we are going to discuss A. Calculate the current in the circuit. Okay. In order to calculate the current, we need the impedance of the circuit. That's that is what I is equal to V by R. No, I is equal to V by R, Ohm's law. But the resistance only here we are calling it as impedance because it is the resistance present in the circuit due to the resistor and capacitor. That's why it is called as impedance, right? So we need the resistance or impedance of the circuit here. It is Z is equal to square root of R square plus XC square formula. XC is equal to 2, actually it is 1 by 2 pi nu c. Actually it is 1 by omega c. Omega is equal to 2 pi nu. But here, in place of writing 1 by 2 pi nu c, we put here minus 2. See here. See this. So R square is as it is, but plus in place of XC we have written 2 pi nu c whole power minus 2. Observe carefully. Here square only, but here minus 2. Okay, right. Now see here. In place of this square root, just we are going to substitute the numerical values, right? We are going to substitute the numerical values. Just in place of R we have to write 200 and in place of 2, okay, right, and it is 3.14 and nu is 50 and C is 15.0 into 10 to the power of minus 6 farad whole to the power of minus 2 whole to the power of minus 2. Okay, right. Now after substituting all these things, see here so from here to here it is a mathematical process, right? First you have to multiply this total terms you have to multiply, and then here it is whole square is there, 200 square, and if you complete this entire mathematics process is a multiplication, you will get it as 212.3 ohms. 212.3 ohms whole square. It is like square root of A square plus B square. Okay, anyhow, if you do this mathematically, the final value, that is what the impedance of the circuit. Impedance of the circuit you are getting as 291.67. 291.67 ohms. Okay, right. 291.67 ohms. This is the impedance of the circuit. Now you can calculate the current. That is what? Therefore, the current in the circuit is I is equal to V by R. Actually, it is Ohm's law, no? It is Ohm's law. But here, resistance means it is not the resistance alone because it is In this circuit there are two things, resistor and capacitor. So that's why here impedance is nothing but the resistance of the circuit. So the resistance of the resultant of resistor and capacitor. That's why it is called as with a special name impedance. Suppose if 3 are there, we have to take 3. That's already we know, right? So when we are in a discussion about the theory, there we discussed. Because here we have only 2 now, resistor and capacitor. That's why we took only 2 here. Right, now I is equal to, V is 220 volts given, divided by Z is 291.67. Okay, that is what approximately equal to 291.5 he has taken. Okay, right, no problem. And that is equal to 0.755 amperes. 0.755 amperes. Okay. Now, see A completed. What he is asking? Calculate the current in the circuit. Right, we calculated. Now, B. That is, calculate the voltage across the resistor and the capacitor. Right, see here since the current is the same throughout the circuit, because these things are connected in series. These things are connected in series. That's why, since the current is same throughout the circuit, we have VR is equal to I into R. I is 0.755 into R is 200 ohms. R is 200 ohms. That is equal to 151 volt. 151 volt. So what is this? This is the voltage. This is the voltage across the resistor. Now voltage across the capacitor, VC is equal to I into XC. I into XC. I is equal to 0.755 amps into XC is 212.3 ohms. Sorry 212.3 ohms. That's we calculated here is equal to 160.3 volt. 160.3 volt. Okay, right. Now see here he asked what is the question he asked? Is the algebraic sum of these voltages more than the source voltage? Right, see here. The algebraic sum of the two voltages VR and VC is 311.3 volts. So you just get the sum of these two, this one and this one. Which is more than the source voltage? No, because source voltage is 220 volts only. Source voltage is 220 volts only, full stop. How to resolve this paradox? Okay, right, see this. As you have learnt in the text, the two voltages are not in the same phase. The two voltages are not in the same phase, full stop. Therefore, they cannot be added. They cannot be added like ordinary numbers. The two voltages are out of phase by 90 degrees. Therefore, the total of these voltages must be obtained by using Pythagorean theorem. That is VR plus C. So that is resistor plus capacitor is equal to square root of VR square plus VC square. That is equal to, VR is this one and VC is this one, and you substitute this value here and this value here and you complete this process mathematically. Then you will get it as 220 volts. 220 volts. Now what is the answer? See this. Thus, if the phase difference between the two voltages, is properly taken into account, the total voltage across the resistor and the capacitor is equal to the voltage of the source. Okay. That is what he is asking. So if S, resolve the paradox. So we resolve no. So we discussed. Okay. That's why what he is saying is, so how to resolve the paradox means we have to find the voltage across the resistor and capacitor by using a Pythagorean theorem, because there is a phase difference. That's why we have to use Pythagorean theorem. Once if you use Pythagorean theorem, then automatically the voltage applied, that is 220 volts, here also we are getting the same. So that only he is saying here. Thus, if the phase difference between two voltages is properly taken into account, the total voltage across the resistor and the capacitor is equal to the voltage of the source. Okay, right. So in this class we discussed two problems. So in example 5, they have given one circuit and he is asking to find, after inserting iron rod into the inductor, after closing the switch, if we insert iron rod into the inductor, what happens to the glowing of light bulb, whether it is increases or decreases or unchanged, right? That he is asking, and along with the explanation, along with the reason. So we resonate, that is what a larger fraction of the applied AC voltage appears across the inductor, leaving less voltage across the bulb, Therefore, the glow of the light bulb decreases. Okay, right. Next problem. In example 6, they have given one problem. They have given the situation where resistor and capacitor are connected in series to the AC source, and it is the applied voltage, voltage applied across the AC source, and it is the frequency of the AC source. He is asking to calculate the current in the circuit, and he is also asking to calculate the voltage, across the resistor and capacitor. Afterwards, he is asking one more question: is the algebraic sum of these voltages more than the source voltage? If yes, give the reason or resolve the paradox. Not reason, resolve the paradox. Okay, right. So first given things, and we calculated current. By calculating impedance, we calculated current in the circuit, and then here we calculated voltage across the resistor and voltage across the capacitor, and algebraic sum of these two will become 311.3. So obviously, which is more than the applied voltage, which is 220 volts. How to resolve this paradox means, here there is a phase difference of 90 degrees. That also we have to consider. So finally, by using Pythagorean theorem, we can write the voltage across resistor and capacitor like this. So that is equal to square root of VR square plus VC square, then which will become equal to 220 volts. So at last, what can we say? Thus, if the phase difference between two voltages is properly taken into account, the total voltage across the resistor and the capacitor is equal to the voltage of the source. Okay, right. So in our next class, we will discuss next continuation problem, that is example 7. Okay, thank you.